micro nano education for everyone.
So let me introduce everyone to Dr. Nathan Jackson. He's going to be presenting today on his story of being a MEMS engineer.
So my name is Nathan Jackson. I'm an assistant professor at University of New Mexico in mechanical engineering. So first, my talk, actually, I should have titled it My Journey, because everyone has their own journey. So what I'm going to talk about is not necessarily what's true for everyone. But the highlight that I want to talk about is really that, you never know what your career is going to take you and what path you take. And you'll see that throughout my talk. I started in one area and I ended up, now I'm working in something completely different than where I started. And, so always try to learn, and get the most experience and skills, in what you're doing, because you never know when you're going to need that. Even stuff like that I'll talk about today, you'll see that, stuff I did like 15 years ago, now I'm like, I haven't used it in like 15 years, but all of a sudden now in my research, I'm like, oh, wait, maybe I can use that to solve this problem. So, I'm always trying to solve problems based on the skills and stuff that I've learned in my past experience. So yeah, just to give a brief background on myself before I get into my talk too much. So I got my PhD from Arizona State in bioengineering. So actually all of my degrees are bioengineering, but now I'm in mechanical engineering. In the past, I also did a postdoc in material science and then I was a senior researcher in microelectronics. So, I've been kind of in all the different engineering disciplines. Except for nuclear, really, is the only one I haven't really touched on too much. But my work was on brain-machine interfaces, which I'll briefly talk about a little bit later. And then after I graduated, I went on to work in a microelectronics national institute in Ireland. So it's a third largest microelectronics institute in Europe. And it's the only national lab in Ireland. And there, I first started off as a postdoc and then became a senior researcher, and then I became the MEMS team leader before leaving. So I worked there for about 8 years, and then I joined UNM. I decided to go back into academia, come back as an assistant professor at UNM in 2017. So I've been working in the area of MEMS for over 18 years now, and I've worked everything from design to fabrication, MEMS packaging, characterization, and everything from academic to industry. So some fundamental science to stuff that's actually that's already commercialized. So I've worked a lot with different companies, as is shown here: Analog Devices, Intel, Philips, Aerogen, Sorin, a lot of medical companies, some semiconductor companies, all over the place. My research is really focused on smart materials, how to integrate these materials into MEMS devices, and then also making these into applications. So I'm very much an applied researcher, so I try to make things that are going to be useful in the near future. So I work a lot with energy harvesters, aerosol generators or atomizers, acoustic resonators, which are sort of the big area for a lot of MEMS devices right now. And I do occasionally go back to my foundations in bioengineering and do some biomedical stuff, although that's sort of limited right now. So the outline of my talk, first, I know some of you have heard some of the other seminars and stuff, but I'll just go through a brief background of what MEMS are and some of the jobs that are available, some of the market analysis, why you might be interested in a job and a career in this area. And then, talk about how multidisciplinary, this MEMS area is. And then the heart of my talk, though, is going to be on my journey. So where I started in MEMS, I'll go through some of the research applications that we did, and then, what I'm working on now in the last, 10 years or so. And that's sort of going to be the basis of my talk. So I'll try to give a high level overview of most of the talk, of most of the areas that I'm working on. So the first thing is, so what is MEMS devices, or what are they? So MEMS stands for micro electromechanical systems. Alternative names are actually microsystems or micro machines. These are, again, the same thing. I actually prefer the term microsystems over micro electromechanical systems, because not all MEMS devices have electro or mechanical components, but they usually are, again, all on the micro scale. So these are all small scale devices. So this is actually images taken from Sandia. They were one of the big people working in the MEMS area. So these are some gears, and these are all at the micro scale. So these are things are the fabrication processes. These are all stuff that's smaller than than human hair. Human hair is about 100 microns in diameter. Some of these fabrications, some of these components are, again, 1-2 microns in length or in dimensions. So therefore, again, if you were to cut a human hair into about 100 different pieces, that's about the sizes of a lot of these things that we're working with. So your first question might be, why are we interested in MEMS? So MEMS, one reason is because they are smaller. So you can fit more things in a smaller space. They are usually lower cost, and that's because we do batch fabrication. So so the fabrication process is similar to like how Intel and stuff make their transistors. So we make lots of devices at once. Also, when we're talking, a lot of these devices are sensors. And some of the sensors, again, when we go to small scale, we can make them more sensitive. So therefore, we can detect, smaller amounts of, whatever we're trying to sense, such as, for instance, biomedical. People have made sensors that can detect down to a single virus, so single molecules. And then, also when we get to the small scale, these are usually have lower power requirements. So then we don't need as much power to power these things. They also operate at faster response time. So think of an airbag. So one of the earliest MEMS devices is an airbag deployment. And again, you want these to operate very quickly. So as soon as it detects, a crash coming, it deploys very fast. So you want these things to operate very fast. And even for your phones, MEMS devices in your phones need to operate at high frequencies, in the gigahertz range. And really the other reason with MEMS is that we're able to integrate this with microelectronics. So a lot of times we try to make them compatible with how they make transistors, so that way we can integrate them and have everything all in one. And there's a lot of other numerous advantages depending on the applications and different devices as well. So where are MEMS used? So the first big boom of MEMS was really in the automotive industry. So in the 90s, and it still is a very popular area. There's still a lot of MEMS, sensors and components in automotive. And actually this is still increasing. I mean, if anyone's bought a car recently, they have lane detection, they have all, there's so many different sensors, to try to make it more safe and less likely to get in an accident. But also they're adding, such as tire pressure sensors, stuff for your engine. So, but these were popular back in the 90s and still continue to increase as well. The next big boom was consumer electronics and your phone. So your phones are the main one that's been the main target over the last 15 years. Most people have a smartphone now, and if you bought anyone recently compared to the ones back in 2007, 2008 when they first came about, again, the functionality and the amount that they can do is increased quite dramatically. And this is what's driven a lot of MEMS devices. Your phone right now has, quite a few different MEMS sensors and actuators to make it work. And actually the MEMS device, the duplexer, which is an RF MEMS device, that was really kicked off the development of MEMS duplexers has really kicked off the area of smartphones. So what's going to be the next big boom? The next big boom is really going to be in the area of the Internet of Things, which is currently ongoing. So we want information. We live in a time where we want information on everything. We want smart buildings. We're talking about when you enter in a room, you want, okay, the air conditioning to come on, or you want, a certain, potentially changing the wallpaper, changing the color, changing the lights, to detect who's coming in and everything else. So, we want smart buildings. We want to be able to detect, gas, carbon dioxide, if there's a leak, carbon monoxide, all these things we want to be able to sense, and not only in smart buildings, but we're talking about agriculture, we're talking about roads, structural health monitoring. We want all these things. And in order to do this, we need, we need MEMS devices to act as the sensors, also the communication systems, and also the batteries and energy harvesting, which I'll talk about a little bit later. So the MEMS market, is quite growing. So if you're interested in a potential career in this area, I'd recommend it. The growth is about 11 to 13% annually right now, compared to ICs, which is about 7%. And in the future, people are predicting that this will grow about 15 to 30% annually over the next 10 years. And this is a bunch of different areas. I'm not going to spend too much time on this, but you can see the areas that are gaining a lot of interest. For instance, this bottom one, this is BAW filters, which stands for bulk acoustic wave filters. And I mentioned the phone, the smartphone. So this is really these type of filters are what's caused the smartphones to come about. And you can see about 2007, when the smartphones, that's when they were, just starting. But over the time now that phones have become so important and everyone has one, you see the huge demand has increased quite a bit. And some of these other areas are more areas, or just they're starting to get into. This is stuff that we've been doing research on. So I'll talk a little bit about some of my research in energy scavenging and some of these other areas, drug delivery. But these are just new areas which we're hoping will continue to increase, and these will be the next big thing. So MEMS, though, MEMS is highly interdisciplinary or multidiscipline. You can't be an expert in every single one of these, but really, it requires, knowledge of all working STEM disciplines. The name itself, yes, has mechanics in it and electrical. So, those are two of the main components, but you also need chemistry. Like when you're making these devices in the microfabrication, you're doing photolithography, you're doing etching, you're dealing with very dangerous chemicals, and you need to know, again, how to work with these. A lot of times, a lot of MEMS devices use heat, and I'll talk a little about these. During my PhD, I worked on electrothermal actuators. Some use fluids, some use magnetics, some, even math, so a lot of the people working in the like the industry, design of experiments. So your statistics is extremely important to industry. So again, mathematics people are very important, and even nanotechnology or even quantum mechanics it can be important, because the next generation, I'm talking about micro electromechanical systems, but the next generation is really nano electromechanical systems. So going to nanotechnology and down to the nanoscale. So what kind of jobs are there? There's a lot of different jobs. Some of them, the ones I list here are some common jobs. First, there's the typical jobs, which are, fabrication, process engineer, technician. So these are the people in there actually working, making the devices. And then there's MEMS device designers. So these are the people maybe sitting at a computer. So these are more computational people. They would be designing the masks. They would be, developing the layout, the structure of their different devices, and these are, again, a lot of computational people in this area. And then there's characterization or test engineers. And then there's also MEMS packaging. So a lot of people, especially in academics, don't really know too much on MEMS packaging, but packaging is really about 80% of the cost of a MEMS device goes into packaging. And that's because there's no standard packaging. In ICs, there's standard packaging techniques, but in MEMS, every MEMS device is different. So it requires different packaging. So that's why it's very unique. And packaging is one area that I'll briefly talk about in my, because I worked on this during my PhD, but it's often overlooked in academia just because it's hard to get funding to do MEMS packaging. But other jobs that you might not associate with MEMS or in this area is stuff like microfabrication equipment. So the equipment we use to make these devices, such as like deep reactive ion etching, furnaces, photolithography systems, even testing equipment, all these, so building these equipment is quite important and to making devices and characterizing these. Another one is clean room infrastructure. So these are people that help design clean rooms and also help keep it operating. So the clean room is a complicated system. You know, you have to control the humidity, you have to control temperature, you have to control the particles. So, you know, keeping these systems operating, you know, is also quite challenging. And actually, a lot of times the equipment people, people fixing equipment in there for companies will actually probably make more money than any of the engineers almost doing the fabrication process, because, you know, it's so useful. Because if the equipment goes down, say at Intel, you know, that's money. You know, they can't process wafers if there's some equipment's down, so they need things to be up and working, you know, as soon as possible. So a lot of times you might be on call 24/7, but again, you're quite valuable. I know a lot of MEMS engineers who have gone on to work in sales, so selling MEMS devices or even wafers, or, you know, a lot of these materials. So yeah, so you can work in sales. Quality assurance, again, very important, especially in bio-MEMS area, trying to get things FDA approved. Robotics, so a lot of times, like places like Intel, you know, process engineers don't actually ever touch the wafers, so they have robots that do all this stuff. So then you need the, you know, people designing and developing these robots to handle these wafers and to handle the processing. Machine learning is becoming very popular, you know, and potentially in the future a keen interest in MEMS area and microfabrication. And there's, like I said, there's many more jobs, but this is just to give you a sort of a rough overview of some of the job potentials that are out there. In short, basically, if yeah, I'm sorry, moving my cursor. If you have a discipline or knowledge in STEM, you know, there's a job opportunity in MEMS. You know, any STEM discipline that you're working in, there's potentially a job for you in MEMS. So now I'm going to talk to you about sort of my journey, which, like I said, should have been the title of my talk, my journey as a MEMS researcher. First, before I go into my journey, I'm going to tell you where I am now, and then I'll show you, and then I'll go through sort of the history of it. So my group my group's called the SMART group. So Smart Materials and MEMS for Applied Research Technology. And we really work on the 3 pillars in MEMS, which are materials, design, and fabrication. So in MEMS areas, we do a lot with a bunch of different materials, and we're always trying to develop new materials, new smart functional materials. And then but then we can't just develop the materials, we have to develop how are we going to introduce them into our fabrication process and make sure they're compatible with other materials or other fabrication processes. And then once we do that, then we can worry about making devices. So in these 3 pillars, you know, we develop new materials. Designing, this has to do with developing new like finite element modeling, which I won't really talk too much about in this talk. But again, it is a huge area of interest, and it's more computational, you know, design. And then fabrication is always an interest, and we're not just trying to take these materials and fabricate something, but we're also always trying to develop new fabrication techniques, new methods of making new materials, and how to make them compatible with current fabrication processing steps. And my research mostly focuses on piezoelectrics, so you'll see this come up quite a bit. But I've also worked a lot with other materials, which I won't really talk about, such as magnetics, hydrogels, polymers, elastomers, liquid metals, stuff like this that we try to develop into different devices. So this is sort of an overview of the current applications that my research is working on. So I won't, you know, I'll briefly talk about some of these in this lecture, but just, yeah, kind of at a high level overview. One of my big areas of interest is in energy harvesting. So this is kinetic energy harvesting, so at the micro scale. So we're working on trying to harvest small amounts of wasted mechanical energy. So, and what I mean by this is, so there's everything around us is vibrating, you know, our buildings, you know, our desks, everything, or cars, everything has some type of vibration. It might be small, so you can't feel it, but again, there is some vibration there. And so we want to try to harvest energy from this And the main reason for this, which I'll talk about a little bit later, is to power like the Internet of Things. So that way we just need small amounts of power. I'm not talking about like I'm not talking about powering like the whole city or something like that, like wind turbines and stuff like that. We're just trying to harvest small amounts of energy just to power a sensor. I also do a lot of work in biomedical sensors, which I won't really talk about in this lecture too much. We do a lot of work with actuators. These are gas pumps, drug delivery systems, microphones for your phone, micro speakers, stuff like this. And then with materials, we do a lot with I'm trying to develop more flexible, or even go one step further into stretchable electronics. So right now we're in flexible, but we hope to then eventually go to stretchable electronics. And I'll explain why we're interested in this a little bit later. I do a lot of work with acoustic resonators. So these can be anything from ultrasound transducers. We work with gas sensors. These can also be particle sensors. This is combined kind of with medical sensing as well. These are also RF MEMS devices, so like filters and stuff that filter transmissions from your phone. And a lot of different things there. I'll briefly talk about these, but not in too much depth. And then tactile sensors. So we're working on making new touchscreen, devices, smart gloves for surgeons, and all these kind of different applications. And there's other applications that we're working on too, besides these. So that's kind of where I am now. Now I'm going to talk to you about where I started. So my first experience in MEMS started actually as a graduate student. So you guys are already way farther ahead than I was. When I was an undergrad, I knew nothing about MEMS. I didn't know what MEMS were. I didn't know anything. I never heard of the word MEMS. It wasn't until after I graduated and I was looking at where to do graduate work. And then one professor from Arizona State, Dr. Mithaswamy, my former advisor, he showed me a video. I was like talking to him, like, hey, I was maybe interested in your research. I want to see what you did. And he showed me a video of a MEMS device from Sandia. And from then I was sold. I knew that that's what I wanted to work on, and I knew I wanted to work with him, and and that's where I started. So my experience was in, like I said, my master's and PhD was in brain-machine interfaces. So we were using movable MEMS implantable microelectrodes that we implanted in the brain to be used as a brain-machine interface. And I'll explain what this actually is in the next slide. So this has been an area of brain-machine interfaces, especially electrodes being implanted in the brain, have been an area of interest by many researchers, neuroscientists, and engineers for over 50 years, since the 70s. And really, the reason why we're interested in this is mostly for neuroprosthetics. So people that have maybe that are paralyzed from like the neck down, they don't have much function. They can't really do much. They can, they breathe, and that's, and they're more in a vegetative state. So we want to try to give them some functionality. So if we can try to implant electrodes and tell what they're thinking, their brain is still intact, their brain works. But then, if we can then use that as signals to understand what they're trying to do, then we can use that to control like a robot, like a robotic limb, or a wheelchair for someone who's completely paralyzed from the neck down, or a computer. So you can move a mouse cursor or something like that. Now, this is a very complicated process, and there's a lot of different engineering that is required to get this to work. My area of research for my master's or PhD was in just the electrodes. So just implanting these electrodes and trying to get an electrical signal out of the brain. Then there's a whole nother group I'd be working on signal processing, the robotics, all that kind of stuff. But that's a whole nother area. So we're just focused on just trying to implant these electrodes and get this, try to get some signals out of the brain. Like I mentioned, this work started really in the MEMS area. It started in the 70s at the University of Michigan, where they were working on, Kensal Wise developed a silicon-based electrode that he implanted. And then, the work's still going on there at the University of Michigan in this area. And they've advanced quite a bit from these single electrodes to, multi-array electrodes with integrating it with electronics and wireless sensors and everything else. University of Utah is also another one that was that's very big in this area as well. Some challenges, though, with these current devices, and like I said, research is still going on even 50 years later. So, I mean, it's still not, we still haven't even perfected or optimized these devices still to this day. And that's because there's numerous challenges. There's challenges with mechanics. These are, for instance, these are usually silicon. So silicon is a very stiff material. So implanting that in the brain, which the brain is basically like jello. It's it's constantly moving. The brain is not static. It's moving inside your skull. Again, micro motions, but small amounts of movement. But if think about this though, if you stick a metal fork into jello, you're going to get, eventually you're going to create tissue damage, and that's what happens with these devices. So, you can create tissue damage or bioincompatibility, and this causes scar tissue to form around these electrodes, which is a process called gliosis. And when these scar tissues form, this acts as a big resistor or impedance on these. And when you're trying to get microvolts, signals out, basically it causes your whole system to fail. You won't get any signals out of your device. So what we came up with, along with other people, so MIT and Caltech were sort of the first people to look at this. They came up with movable electrodes. So once this gliosis forms, can we move the electrode through the gliosis, and then we're able to record for longer periods of times? Because right now, a lot of these things might fail in a couple weeks, and that's why they're still not really used in humans yet. That still is sort of in animal stages. So they tried to come up with these movable ones, but the way they had these movable ones is they used big actuators. So these things, I think the size of this, I mean, you can see 10 millimeters. So, you can figure out, these things are a couple inches in height. And same thing, you see it on the mouse here, which if you were to scale this up to a human, again, you can imagine, okay, you have this huge chamber sitting on your head. Well, that's not very practical, is it? So what we came up with is, can we make a movable MEMS device? So make this much smaller, and then, adds more practicality. So we partnered with Sandia National Labs using the Summit 5 process to create these movable electrodes. So this is one of our chips. So this is about 3 millimeters wide. So each one of these electrodes, which you see here, is about, I think it's about 50 microns. So it's about half of the size of a diameter of a human hair. And so these are polysilicon electrodes, which come off the chip. You can't quite see it because I used the black, horrible, I shouldn't have used the black background, I should have used the white or something. But the edge is right where I have my laser pointer here, is where electrodes are coming off the chip. And then we'd implant it into the brain of an animal. Now, we used electrothermal actuators to cause these things to move. So how these work, so if you apply electrical, if you apply a electrical potential to some conducting material, such as polysilicon, what happens? So you apply current through it, it's going to heat up. And what happens when a material heats up? It expands. So if you design these to expand in a certain way, for instance, this one, so we cause it to, so we're applying a voltage here and it's heating up and expands. What happens is it can grab a hold. We have little teeth sort of on these electrodes. So it comes up, grabs a hold of the next part. And then when we release the voltage, we reduce the heating, and it pulls it down. And this happens very quickly, since, remember, I said at the MEMS scale, things happen, it's fast response. So heat transfer in these devices is very quick. So it takes, milliseconds to transfer these. Let me see if I can get the video. Okay, so here's a video of one of our device working. So here's the probe. Eventually, so you see this kind of shine a little bit here. So the shining is the heat going through it. So it's heating and it's moving. And then you see this actually, if you pay close attention, you can see it move. It's moving in 8-micron steps. If I ran this movie or this video long enough, eventually you would see it come off the edge of the chip, and but we can move in very small increments. Let's see, and sure enough, we demonstrated that this works. So we were, at one point we got no signals from our brain. Then we would move it. This is moved, and then like 10 seconds later, after moving it, to a new location, we were able to pick up signals. So we were able to increase the longevity of our device from 2 weeks of getting signals to over 6 months. And that's what led to me getting my PhD. Other work that I did during my PhD was in the area of packaging. So I worked a lot with MEMS packaging. Yeah, and this is sort of what led me to my next step in my career, working in the National Institute from my work in packaging. I'm not going to go through the packaging too much, but again, I already said MEMS packaging is a extremely important area, and again, just showing how we can get down to smaller scale packaging. To have flexible packaging as well. Yeah, this is the only thing I wanted to say on this slide. So this was a side project I had for my PhD, where we were using ultrasound to stimulate neurons. We wanted to see if basically if the imaging ultrasound could actually stimulate fetal neurons, and we demonstrated this. We were one of the first people to work on ultrasound stimulation. And this is what sparked my initial interest in piezoelectrics, because we're using piezoelectrics to create the ultrasound transducer. But my role was more on the neurons. So this is a way that we basically took neurons, instead of putting it in the brain, we took neurons from the brain and put it on these devices to look at how individual neurons worked. So now I'm going to talk to you about my area and my research area of piezo MEMS. So like I said, every story has a beginning. So everyone always says, like, well, how did I go from working in the area of bioengineering to the area where I can say smartphones and stuff like that? Well, after I got my PhD, I got hired on to work at Tyndall National Institute. And our project was on developing an implantable wireless sensing system to monitor physiological parameters such as restenosis. So restenosis is where you have basically, if you want to implant a stent because you have a clogged artery, restenosis is the reclogging of that artery. So if you have a stent in place, you have reclogging of the artery. And if this reclogs, then you have major issues. So we wanted to try to detect this restenosis so that way you can go see the doctor if you need a new stent put in. To do this, we needed a sensor, which we developed a sensor that was not too difficult. We had to communicate, so we had to communicate outside of the body. We had to develop the electronics to transmit this, and then we had to develop a new stretchable packaging or interconnect, and that was my job. But we were able to do this. We were able to accomplish all these. The one thing that we had a challenge with is power. How are we going to power this device? It's implanted in the body. How are we going to power this? We eventually came up with the idea of using piezoelectrics. So we could have a piezoelectric material like hanging in the blood flow. And as the blood passes, it's going to cause this to bend, and we could harvest energy from that. Now, we never actually got around to implementing it, just did some modeling and stuff like that with it. But this was what sparked our interest in energy harvesting and piezoelectrics. And eventually we got the interest of companies such as Analog Devices, who was like, okay, they weren't interested in really the biomedical aspect of it, but they were interested in the energy harvesting aspect. And can you use this to power other applications? So the first part now of my talk, is really of my research is going to be on the piezoelectric materials. So I'll just briefly go through this really quick. So I don't want to spend too much time on piezoelectrics. But piezoelectrics, they've been around for quite a while. There's still a lot of research going on in this area. But the main reason why I'm interested in this is because they have two different, they have a direct effect and a converse effect. So piezoelectrics, basically, if you apply a force or if you stretch it, you can get a voltage readout. So in this way, it's very good as a sensor. If you put a particle on these, you will get a voltage change. So you will get, so it's very good as a mass loading sensor, for instance. On the other hand, it's also good as an actuator, because if you apply a voltage to this, you can cause it to either stretch or compress. So in this way, it's very good for MEMS because it can act as a sensor or an actuator. Another reason why I'm interested in piezoelectrics is it's really, a lot of people are saying it's the next big thing for MEMS devices. And a lot of it, the interest has started, like I said, with the bulk acoustic wave filters used in your phones, and also inkjet printers. This is what started the area of piezo MEMS. But now there's a lot of people looking at piezo MEMS. In the future, it looks very bright. People are looking at it for your microphones, for your phones, speakers, fingerprint technology, gesture recognition. So there's a lot of different areas. And so this is one of the reasons why I'm interested in piezo MEMS. So the first, though, like I said, the first fundamental to piezo MEMS is creating the material. So we work on a lot of different materials, and because there's so many piezoelectric materials, and each one has their own advantages and disadvantages, and are good for certain applications and bad for other applications. But we're working on not only in developing these materials, but also enhancing the properties, and even going one step further and trying to create new piezoelectric materials, and mostly focusing on ones that are compatible with microfabrication, so we can use them in MEMS. So we deal with some ceramic materials like aluminum nitride, zinc oxide, PZT, stuff like this. But we also deal with polymer piezoelectrics like PVDF, and trying to add nanocomposites to these to make them more compatible. And then we work with trying to create new piezoelectric materials, new polymer or stretchable piezoelectric materials. One of my big areas of interest over the years has been on, like I said, developing flexible piezoelectric materials. So I worked with aluminum nitride, which is compatible with current fabrication process, and that's actually one of the main materials used in your phone for a lot of the sensors. But yet it's a stiff material. It has a Young's modulus of about 350 gigapascal, so it's very stiff. But I was interested in trying to make it flexible. So I developed, back about 8 years ago, I developed a process for making it flexible by depositing it onto a flexible substrate. The quality of the material wasn't as good. So D33 is sort of how we determine the quality of the material. So it wasn't quite as good as we can get when we deposit onto a single crystal silicon, about 4 times less. So we weren't satisfied, but it was still better than anyone's done at the time. But then I developed new methods of depositing onto different polymers, more crystalline polymers, and trying to alter the material properties of these polymers to promote the aluminum nitride growth, to enhance the properties. And we were able to get much better, quality aluminum nitride. And now these can be used, and they're quite often used and cited in a lot of different academics and commercial applications now, where people are using this type of polymer piezoelectric materials. So my group, like I said, we focus on creating flexible and stretchable piezoelectrics through different techniques, such as modifying the polymer materials, the crystal structures. We try to add composite materials, so adding nanocomposites to these. And we also can create a kind of hybrid piezoelectric materials as well. Other materials that I work with other than piezoelectrics are stretchable materials. So I try to develop new stretchable elastomers, and trying to integrate them with liquid metal, such as Galvanstan. So we were using these for tunable MEMS devices. So these were introduced as tunable antennas. So that way we could actually tune the antenna. So if you want to transmit at a certain frequency, and then you want to change and transmit at a different frequency, you don't need multiple antennas. You can actually use just one antenna and change the frequency at which you tune it. I've also worked with smart hydrogels. And I see my time, so I'm actually going to probably skip this area for now. But yeah, these were smart hydrogels, basically the opposite of a stent. So now I'm going to talk to you about some devices that we work on. So one is energy harvesting. So I've kind of already answered these initial questions. So the initial question is, why are we interested in MEMS energy harvesting? I've briefly talked about that. The answer is the Internet of Things. Like I said, we want information on everything. So what are these Internet of Things? What is it? It's a wireless sensor network. So all these Internet of Things have sensors. They all have a microcontroller, a transceiver, but more importantly, they all require some type of power. Well, right now, these power come from a battery. So all these things are powered by a battery, but batteries, as you know, need to be replaced. And sometimes these, when you're talking about a couple devices in your house or something, that's fine. But when you're talking about having trillions of devices around the world, that's a lot of batteries. Now, the battery industry would probably love this, but ultimately it can cost quite a bit to change the batteries. For instance, if it's in a remote area, such as like on the Golden Gate Bridge or something like that, if it's at the top of that, again, paying someone to go up there just to change a battery can be quite labor intensive. So we want to create a self-sustaining system that can harvest energy from the ambient environment, such as through vibrations. Which is shown here. There's multiple energy harvesting techniques. There's photovoltaic, solar cell, thermal electrics, but again, we're interested in movable, so vibrational or kinetic energy harvesters. And even in kinetic energy harvesters, there's multiple ones, but we're targeting piezoelectrics. And the applications that we're targeting are mostly in the area of structural health monitoring, automotive, military applications, such as drones, industrial use, healthcare. But again, smart buildings, stuff like this is what we're sort of targeting. So initially, when we started working on this is about 10 years ago that I worked on this. First we had to develop the piezoelectric material. Okay, we did that. Then we had to develop how to integrate it into the device, and we had to optimize the device. So in the first couple of years of our research, we weren't targeting a specific application. We were just trying to get the highest power density that we could. And we showed that we were able to get up there with the best power densities, up to about 2.5 milliwatts per centimeter cubed, which is pretty good. But one thing, this is in an ideal lab setting. Once you go to actually applying this in a real life application, your power, your values are going to drop quite a bit, just because there's unknowns, there's uncertainties that happen in real life applications. So there's 4 major challenges associated with MEMS vibrational energy harvesting. One is low power density. You always want to harvest more energy, so that way you can power more systems. So that's always one problem. The other problem is bandwidth. So these devices have a very narrow bandwidth of about 1 hertz. So what that means is that if this is your resonant frequency of your device, but then all of a sudden your frequency of your source, your vibration, is over here, is saying highlighted in blue, you can see our power has dropped quite significantly. So we're now basically we're not harvesting enough power to power our sensor at this point. And that's sort of the one big challenge with this. Also, reliability is another big challenge, because to optimize the amount of power, you want to optimize the amount of stress and the amount of displacement. Well, the higher the stress, the more likely your device is to break or fail. So it's a trade-off between trying to harvest power and trying to make something reliable and last for a lifetime. So people have tried to increase the bandwidth, but when you increase the bandwidth, you drop the peak power. So yes, this power now is better than this, but it's still not as good as up here. So then again, power density becomes an issue. So what we're working on is trying to develop new methods of increasing bandwidth without dropping the power, which is actually quite difficult. And we do a lot of nonlinear dynamics and stuff like that to try to accomplish this. Another method is, can we tune it? So now that our resonant frequency is here, if our vibration source is over here, can we change the resonant frequency of our cantilever device to move to this is actually very difficult to implement. I'll talk about one brief example of how we're working on this. There's other methods that we're trying, but again, since this is being broadcast, I don't want to, can't talk to some of them are confidential. So, but I'll go through some of these. Of course, the ideal application is if you have a vibration source that doesn't change. Of course, if anyone can think of a vibration of an application where the vibration source is never going to change, please let me know. There's not very many applications that do this, but if you can, this is, that would be quite important, because then we could easily make a device to operate in that application. This is just showing, this one was actually made for a smart building application, but this is showing, so the length of this is about 7 to 8 millimeters in length. So it's actually a big MEMS device, relatively large. And the reason why it's that large is to get to the low frequency that we need. But you see our power dropped quite a bit, from 2.5 milliwatts to about 1 milliwatt. And that's just because now we're actually trying to apply it. We're trying to target a specific frequency. And that just causes, all types of problems. One of the big problems that we've worked on energy harvesting for a bunch of different applications, but I want to target one application specific. One was on leadless pacemakers. So all of you are probably familiar with pacemakers. So they typically have, like this, that has all the electronics, the battery, and then you have leads going into the heart. And this is usually implanted in the clavicle. Well, the latest generation of pacemakers is leadless pacemakers, where they implant these into the heart. And there's actually some FDA-approved ones already. But these FDA-approved ones, they require batteries. And this is such a small capsule. I'll show a size on the next slide. That, again, the amount of batteries that you can fit in there is very small. So again, the lifetime of these might not last that long. And unlike these other ones, you can't go and take these out. They're screwed into the heart wall. You can't really go and take them out. But you ask, well, why did they ever go to the leadless? Well, the main failure mode for these is the leads. So people can play, you can feel these underneath your skin and they can play with them and they get tangled up. And so these cause failure. So this is a way to get around that and to not cause failure. So what we came up with was the heart is a very good mechanical pump. So if we can, and this is a vibration. So if we can actually put our like a energy harvester in here, such as cantilever, then we can, as we create a mechanical movement, vibration, we can actually harvest energy from that, and we can maybe increase the lifetime of the battery. I'm not going to go through all of the results and stuff, but basically we were able to get decent power, about 5.62 microwatts of power from this. And this just shows the capsule with our device in there. And it needs to be about double that to actually be useful. But of course, there's also the lifetime, would this work for, 20 years or something like that? Those kind of tests still need to be taken up. We haven't done long-term reliability testing or anything like that, but we're in the order of the ballpark of where we want to get with the power anyways. Yeah, I'm working on different methods of increasing the bandwidth, but I see my time, so I'm actually going to kind of skip this slide for now. Tunable MEMS devices, I mentioned this. So one method that we used to tune the MEMS devices, we took on our cantilever, we put a new photoresponsive material. So this is a material that changes its mechanical properties as you shine different lights on it. So as we shine UV light, if we shine green light, it changes its mechanical properties. And if it changes its mechanical properties, it's changing the stiffness of the cantilever. And if you change the stiffness, then you change the frequency. So here we showed, here's our initial frequency of our cantilever. And then after we shined it with UV stimulation, we were able to tune it. And again, not a lot, not a large tuning, but again, and the amount of tuning that we could get is dependent on the intensity of the light that we shine on that. Another area that I work on besides energy harvesting is aerosol generators. So aerosol generators are quite, you can think of these as like, humidifiers and stuff like that at home. But we were using them initially for drug delivery. But now we're looking at using them for different techniques. The reason why we're the first people to try this at the MEMS scale. And at the MEMS scale, the reason why we're interested in developing these at MEMS scale is that we can add functionality. So we can add different sensors, we can add different components to this, to where we can now use these in different applications, not just for drug delivery. So this just shows an example of this is like a saline for someone who has asthma. So this is like a butyrol that's being atomized. Just showing that these things work. But now we're looking at using these in different technologies. I can't talk about all the technologies due to patent issues, but right now we are working on, like I said, inhaled drug delivery. We've shown that we can do this. We're also looking at using this for advanced manufacturing. So we're actually using a MEMS device to create new MEMS devices. So we use this to spray, for instance, photoresist into large topography surfaces, like it's found in MEMS devices often. And we get a more conformal coating when we do this versus if you do normal spin coating where all the photoresist just sits at the bottom of this trough or channel. We can get more conformal coating. Acoustic, yeah, okay. See, I'm almost out of time, but I only have a couple more slides. So acoustic resonators. So I mentioned these are what's found oftentimes in your phone as, RF MEMS for filtering out transmission lines and stuff. What we're working on now, we're working on making them for that, enhancing properties, but we're also working on, can we use these same type of sensors for other applications? One is biosensor. So I'm going back to my biomedical, again, back to the history that I had, that I did 15 years ago. Can I use this technology that we've developed for smartphones and use them as a biosensor? So for instance, this is how even some of your COVID sensors, some of the ones being developed by some of the companies are actually made using this type of technology. Some future projects, we work a lot with microneedles. So these are things that, like, for drug delivery. So again, there's a lot of people working on this area, trying to create different types of needles. These are painless needles. So these are ones that just go barely into the skin, so they don't go deep enough to hit the nerve cells. So they're painless drug delivery. So you could use these for delivering vaccines or delivering glucose for people that have diabetes and stuff like that. Other areas of interest in the future, or that I'm currently working on, is taking piezoelectric materials and making new microelectronics, making new ferroelectric field effect transistors. So these are, for instance, for memory devices. We're interested in using these technologies as microthrusters for aerospace applications, developing new ultra-sensitive biosensors, new touchscreens, as I mentioned. All using the same materials, a slightly different way. And even micro robots. So I had a master's student back a couple years ago who was looking at trying to mimic jellyfish movement using piezoelectrics, and the hope that we could, implant these robots maybe in the body to deliver drugs. That's probably a little bit more far-fetched. Ideally, what we were thinking is, could they go through pipes, liquid pipes to fix cracks or something in the pipeline? For instance, for oil pipes or for nuclear pipes, because these can handle high temperature applications and stuff like that, or reactive radiation also. So in summary, so there's a lot of different jobs out there in the area of MEMS. The market is great. So that, if you're interested in a job in this, the potential, career advances throughout your lifetime is quite high. You can also, like I said, if you're interested in any area in STEM, I know people often ask, well, what type of, discipline should I go into? Electrical engineering, mechanical engineering are obviously the two main ones, but even chemical engineering. I have students in chemical engineering. I have students in math department, working for me. So really all these things, machine learning, computational, computer, even chemistry, even biology, people working in bio-MEMS. So there's a lot of different areas. And every MEMS engineer or technician has their own journey. I mean, if you talk to Dr. Plyle, if you talk to any of these other people, they all have, a different story of where they started and where they've gone. But you never know where the journey is going to take you, and it can go anywhere. And I don't know what the next, 20 years of my career hold. We'll see. But yeah, but basically, if you're interested in if you have a strong interest to learn about new technology, new disciplines, you want to be very diverse, then I would say again, MEMS is sort of, and microfabrication is sort of the right field for you. And I just want to sum that up with a couple quotes that I like, that I think are relevant to MEMS. One is by Yogi Berra. So if, I don't know, some of you might not know who Yogi Berra is, but old baseball player. But he had all these famous idiotic quotes, kind of.
And then he's um, asking about the transition from industry back into academia.
Yeah.
So
Yeah.
I'm sure you've read the question already in the chat box. So if you could address that, that would be.
Yes. So yeah, it's been a big well, so I've had two challenges. Going from industry to academia, but also going from European to US, So yeah, because the European funding, for instance, for research is quite different. They're very much more applied. Is US is much more fundamental science. So it's definitely been a challenge there. As far as transitioning from industry to academia, I use that to my advantage. So, like when I teach my courses, I try to, emphasize on more practical, I don't do I mean, we have to obviously do the academic route, the theoretical stuff, but I try to give students, here's the theoretical, here's what, you do in academia, but here's actually what you do when you go and work in industry, here's what they actually use, so I hope that gives my students, an advantage, when they go and try to work and get a job. But yeah, it's been somewhat of a challenge, but it's not that bad. Like I said, it's more about going from applied, getting something to work, thinking something in the industry, you want something to work in the next couple of years, as academics are more, okay, I want something that's, maybe going to be the next big thing in 20 years or something, so that's been sort of the big challenge. But I still try to work on applied and I still work with a lot of companies, even in mine, working with small business loan associations and stuff like that. So.
Yeah, and I think that's real valuable for your students, right?
Yeah, I hope so.
Most of our students end up going into industry or national labs or places like that. Only a few of them end up going into academia.
Yeah, and the stuff you learn, even the practical stuff, is still useful in academia. So I mean, it's still, like I said, I'm a person that I love learning all the time. So I don't think there's, anything that, if you learn something, there's no way that's wasted knowledge, and that's one thing I want, kind of highlight. You never know, like the stuff, as a student, you might think that the stuff you're learning in your course, you're like, I'm not going to use this, but you never know. Maybe in 10 years time, you might. And that's the same thing with me. I mean, I was that way too as a student, and even as a, like, even doing my PhD, like there's stuff that I did when I was doing my PhD that I haven't now done in 15 years, but all of a sudden I'm like, oh wait, now I have a problem with my current MEMS device. I'm like, oh, can I actually use that? I'm like, okay, yeah. And now I can use that knowledge. So, any knowledge is always good, and, try to keep it, in your head. So that way, you can always go back and use it when you need to.
All right. We have some questions regarding clean room processing and that sort of thing. I'm going to refer the person asking that question to the SCME online short courses, and I'll go ahead and put a link in there so you can scme.online. So we have a lot of information on the basics of fabrication, because to talk about fabrication would be another 8 hours. There's a lot involved in that. So it's SCME. Yeah, somebody corrected me. Thank you. I typed my own website. SCME.
Some online.
And then you can also shoot me an email, and I've got resources as well as Dr. Jackson on fabrication. So
yeah, I didn't focus too much on the fabrication. Yeah, because I mean it's a whole nother area, and
Well, this was really good and very informative. But what's interesting is once you get a handle on some of the fabrication methods, you can build a lot of things with it. So it's like having a
Ex-
box of Legos.
Exactly, and that's where I mentioned the side project on the ultrasound transducer, for my PhD. That was just something on this, like, both me and the other PhD students that were working on that. It was not part of either of our PhDs or anything. We were just in the fab, and we're like, wait, we can make this, and we're like, okay, let's try. We just sort of like made these, and then ended up, it's even. And now, actually, like I said, those are actually used in ultrasound stimulation are actually being used in humans now. So the work that we did, that was just sort of a side thing, ended up leading to, stuff that's actually, I know like a psychology professor in UNM is actually using this to look at cognitive, functions and stuff like that, so yeah, it's quite fascinating.
Yeah, and Elon Musk just got into the neural implant business. So
Yes.
letting monkeys control the computer just by thinking.
Yes, and that's all work from, again, starting, like from the University of Michigan. Arizona State was very big into that. I wasn't part of that group, the initial group but they had a paper published in Science, showing that, a monkey controlling a robotic limb, and how actually the robotic limb is actually quicker than so like the monkey, when he thought to grab the banana, was actually quicker than his actual hand. Because again, electrons travel faster than the signals through our nerves. So it was slightly faster than to get the banana. So you could be a bionic person or something. Yeah.
Wasn't that a DARPA project to try to get pilots to be able to fly without having to use their hands?
Yep.
Fly by mind.
Yep, and it's all the same thing. And there's different ones. So we were working on implantable electrodes, but then there's a lot of people working on like ones that sit on top of your skull. But the way that I envision that is almost like a stadium. Like, the one on the skull, like the spatial resolution that you can get is very small. Like you might be able to tell, like if the whole stadium is yelling boo, or something other obscene gestures to the ref or something like that. But like the implantable then is going to, like, if you want to try to sense a single person, what one person in that whole stadium is trying to say. And that's what we were trying to do. We were focused on trying to get a single neuron or a couple neurons, and trying to focus on that.
Fantastic. So, well, with that, I think we should all give him a round of applause.
Yeah, thank you.
Nice job, Nathan.